Welcome to this explainer. Today we are tackling something absolutely fascinating. We're going to demystify a 17th century mathematical principle and show you how it's actually the hidden engine running under the hood of modern artificial intelligence. If you've ever wondered how dry formulas on a chalkboard connect to the AI of the future, well, you are in the exact right place. So let's just dive right into this crazy question. How does a calculus concept taught in high school bridge the gap straight to the cutting edge of tech engineering? I mean, it sounds almost impossible, right? How does a rule discovered hundreds of years before the first computer even existed actually make modern language models like ChatGPT smarter? Here's our roadmap for today. First, the anatomy of a composite function. Second, the step-by-step chain rule. Third, analyzing common errors. Fourth, neural networks and scale. And finally, backpropagation. We're going to start with some super intuitive analogies and then slowly zoom out to look at the massive, interconnected web of neural network optimization. All right, Section 1, Anatomy of a Composite Function, Understanding Nested Layers. To truly grasp the chain rule, we first have to strip away all that intimidating math notation. Forget about x's and y's for a second and let's just look at what a composite function actually is at its core. Let's use a really simple analogy. Imagine you're coming home on a freezing winter day. You're wearing a warm sweater, and over that, a heavy winter jacket. You literally cannot take off that sweater until you take off the jacket first. Mathematics works exactly the same way. You have to mathematically unkeel the outer jacket, your outer function, before you can even touch the inner sweater. So whether you visualize it as winter layers or, say, a Russian nesting doll, the core idea is identical. A composite function simply means one mathematical operation is acting as the direct input for another. Picture a visual function tree, where the results of one calculation immediately become the starting data for the next. That exact nesting is what makes a function composite. Moving on to Section 2, the chain rule step by step, the order of operations. Now we're going to take that sweater analogy and turn it into a real procedural math rule that you can actually apply. If you're ever sitting there confused about which function is on the inside and which is on the outside, just use this simple order of operations trick. Imagine plugging a test number into a calculator. Whatever calculation you are forced to do first, like solving what's inside the parentheses, that is your inner function. It's a great foundational step-by-step trick to always get it right. And here is the crucial takeaway. The rule is this. You take the derivative of the outside function while leaving the inside totally untouched. Then you take the derivative of the inside function, and finally, you just multiply those two results together. Multiplying those gradients is literally the entire foundation of the chain rule. Okay, Section 3, Analyzing Common Errors, What Not to Do in Calculus. Even though the rules sound simple when we say it out loud, students stumble over it all the time. Let's look at some real-world classroom mistakes to see exactly what goes wrong, and more importantly, how you can avoid these exact traps. Look closely at this student's work on an exponential function. Before I give it away, can you spot what's wrong here? The student just rewrote the function, assuming the derivative of an exponential is just itself, but they completely forgot to apply the chain rule to the exponent. As this table brilliantly shows, the absolute most common pitfall when differentiating trigonometric or exponential functions is taking the derivative of the sign or the exponent, but completely forgetting to multiply by the derivative of that inner angle or power. It's like taking off the winter jacket but completely forgetting the sweater exists. You see, the exact same thing happened with polynomials, like in this real test example. They applied the power rule perfectly, but by not multiplying by the inner derivative, which in this specific case meant missing a crucial negative sign, it ruins the entire calculation. Just one forgotten little detail inside the parentheses flips the whole answer. Section 4, Neural Networks and Scale, From Paper to AI Engineering. Now prepare to have your mind blown a little bit. We are transitioning away from high school math mistakes to look at how top-tier engineers use this exact same rule to build modern artificial intelligence. Those simple layers of functions we just unpeeled on paper, they are exactly the same concept as the hidden layers inside an artificial neural net. A neural net is essentially forming a colossal series of nested mathematical equations, where the output of one layer of neurons acts directly as the input for the very next layer. But here's the catch. While you might practice the chain rule on a function with maybe 2 or 3 layers, modern AI models are doing it for literally billions of parameters. To calculate gradients inside these massive multi-layer architectures, engineers require incredible computational efficiency. They need a flawless algorithmic approach. And that brings us to Section 5,
Backpropagation, the engine of AI optimization. This absolute need for massive scale efficiency leads us to the greatest modern application of the chain rule we have today.
Backpropagation is basically this incredibly elegant backward pass through the network. It calculates the exact rate at which each individual neuron contributes to the model's overall error. Engineers need to know, if we tweak this one tiny parameter deep inside the network, how will it change the final output? This algorithm gives them the exact answer. This entire step-by-step AI learning loop relies entirely on the chain rule during step 3, the backward pass. The chain rule is what calculates the gradient, which literally tells the system, hey, to get smarter and lower your error rate, you need to adjust this specific weight in this exact direction. Without the chain rule, modern machine learning as we know it simply wouldn't exist. Ultimately, whether you are an engineer optimizing a massive billion-parameter language model or a student just trying to pass a calculus test, the chain rule is just a beautiful, natural pattern. It reveals exactly how change ripples through complex, interconnected systems. So what hidden patterns in the world around us will you discover next? Thanks for tuning into this explainer.